there are two ways then to price in this model, Black-Scholes-Merton model with two stocks. The usual two ways, either with a partial differential equation or computing expected values. So, you know, in computing expected values, you would just compute expected value of my option is going to be of this type up here, g of s1 of t, s2 of t, and some function of the final values of the stock price, so a European path independent option. And then you discount, but that's deterministic, so you just have to compute this expectation under Q, right? So this you can do maybe numerically by simulation, or if you can solve the partial differential equation, then you have your formula for the option price. So I'm going to stick here to the partial differential equation method. Again, for the same type of payoff, there is a missing bracket here. Okay, so we do that. How do we find the partial differential equation? Well, remember the logic of finding partial differential equation. You apply Ito's rule on the price, and then once you discount, you make the dt term equal to 0. Okay? So that's what I'm going to do here. If you apply the Ito's rule on the price is now going to be a function of t, s1, and s2. Right? So I'm not writing it here, but I really mean that c is a c of t, s1, and s2 of t. And then when you when you apply Ito's rule on it, you have to go back to the slides which give you the two-dimensional Ito's rule. And what happens is, as usual, you have the derivative with respect to time. First derivatives multiply drift, which is rs1 for s1 and rs2 for s2. And then you have 1/2 squared volatility asset squared second derivative with respect to s1, plus the same thing for s2, 1/2 sigma squared 2 s2 squared second derivative with respect to s2 of the price. But then you also, because of correlation, you have the mixed second derivative with respect to s1 and s2 times the volatilities, which is s1 sigma 1 and s2 sigma 2, and then plus also the correlation. Okay? Now this is, if you go back, this is the Ito's rule in this case. And then you have, in the Brownian motion terms, you have first derivatives times sigma 1 s1 and sigma 2 s2. Fine. And then if you discount, what will happen if you discount, right? You will get another minus RC term here, which, and then you want that to be equal to 0. You want it to be martingale, therefore the dt term should be equal to 0. So if you put that equal to 0, you get this partial differential equation down here. Okay? You get this partial differential equation. Fine. What is the boundary condition? The boundary condition is at maturity, the payoff is the function g of s1, whatever s1 and s2 are at that point, so it has to be equal for any s1 and s2 positive. And also, if you are thinking about replication or hedging, because this has to be equal to pi 1 over this has to be equal to pi 1 sigma 1, you get that pi 1 over s1 is as before, the first derivative with respect to s1, and similarly for pi 2 over s2. So the number of shares in each stock are the deltas of the option with respect to those stocks. First derivative with respect to s1, first derivative with respect to s2. The usual delta formula. Okay, so in principle, we know now how to approach this problem. We have the partial differential equation. Either we try to compute this type of expectation using probabilistic methods, or solving the partial differential equation. So let's do an example. So this is a pretty famous example. It goes back early into the 70s. Formula by Margrave. It's exchange option. It's an option to exchange one asset for another. If you think about put and call options, those are also options to exchange cash for an asset. But maybe you want to exchange something else, not cash. So it's simply the maximum between S2 of t and S1 of, and difference S2 of t minus S1 of t, maximum of that and 0. Okay? You exchange S1 for S2 if S1 is cheaper than S2 at maturity. Otherwise, you don't exchange. You keep S1. Okay, it's just paying for your other asset with your original asset. We did it with cash before, but now we are doing it with some other asset. So in this case, I mentioned before, talking about Asian options, that when you add exponentials of random motion, you get mathematical difficulties and you cannot compute things. But actually here it still works. You can still compute the price of the option. Why? Well, this is kind of the trick or the approach, how to guess the solution. You look at what happens at the end, at maturity. So at maturity you have this function, S2 minus S1 positive part. And you factor out S1, and then you are left with S2 over S1 minus 1, positive part. Now if you look only at this second factor, that's going to be, in fact, exponential over exponential, which is nice because exponential over an exponential is still an exponential. So this will look something like a call option, well, on a ratio of two assets, so it's not something financially traded, but mathematically it's kind of a call option with strike price 1 on the ratio of S2 and S1. And then you are hoping, well, maybe this is happening at maturity, maybe something like this will also happen before maturity. It's often the case for these type of heat equations that the Black-Scholes-Merton type, that if you have some property at the end, at maturity, it might hold also before, for times before maturity. So we make a guess, we conjecture that the price at some time small t before capital T, before maturity, is going to be of this form. It's going to be a product of S1 times some function of t and z, where z is a new variable which is equal to S2 over S1. Okay? At this point, this is just a guess. And then you try to solve the partial differential equation from the previous slide. Okay? You compute the partial derivatives of c with respect to t, S1, S2, and the second partial derivatives, the mixed partial derivative. You compute it from here in terms of the partial derivatives of d, and you plug that back into the last formula from the last slide. So just to take a look there, okay, you compute these derivatives of c in terms of the derivatives of d, and you plug it in here, and you will get an equation for d. So I'm not doing the details. You can look up the details. It's not going to be in the material for the course, but if you're curious, you can find books, including my book with Zapatero, and you can look up the details. But what comes up after some calculus and some algebra, it's not too hard. You get that this previous slide equation for C becomes this equation for D. Okay? And the boundary condition for D is simply z minus 1 positive part. And if you look at this equation for D, it is indeed a Black-Scholes type equation with R equal to 0. There is no interest rate here. And with volatility squared replaced by this whole thing. Sigma 1 squared plus sigma 2 squared minus 2 rho sigma 1 sigma 2. Okay? This is the same type of partial differential equation as the Black-Scholes-Merton equation. It's just with R equal to 0 and this as sigma squared. For a call option with strike price equal to 1. So we know how to solve it. We know how to the solutions of this type of equations. So I think I'm repeating that in the next slide. Okay? So it's the D is simply the price of a European call option is strike price 1, interest rate 0, and volatility, I took a square root, so volatility sigma is square root of this. Okay. So we know the formula, and we can find the formula for D, and we just multiply it by S1, and we will get the formula for our exchange option. If you do that, you get something here. The formula is written here. I'm not going to go through it, but it's explicit. So it looks a little bit hard because you are subtracting two random Black-Scholes type stocks and taking positive part, but turns out it's solvable. Okay? It doesn't work for, let's say, 3 stocks or some kind of a linear combination of more than 2 stocks, but it works in this case. Okay, that's it for this set of slides.